Break. This entire week we're going to be doing a 3-lecture sequence on linear classifiers, meaning taking what we learned about linear regression and applying it to classification. And I'm trying out a new way of chopping up the material, which is that today I'm going to talk about predictions, and on Wednesday I'm going to talk about training. And roughly you can think about it like when we use, say, scikit-learn, you create some model class and then you do something .fit and then something .predict. And I think it's easier to actually talk about the predict first, which is what we'll do today, and then talk about the fit on Wednesday. If you think about our 3 steps that I've been talking about several times over, that, okay, first we pick our model, then we pick our loss function, then we pick our optimization algorithm. It's kind of like we're talking about step 1 today and step 2 on Wednesday, in the sense that today we'll just talk about what is the model, what does it mean, but not yet worry about how we're going to compare which model is considered better than another one, in other words, the loss. And then on Wednesday we'll talk about training, loss, step 2, whatever you want to call it. We're currently in the midst of what you could think of as part 3 of the course, in the sense that we had the first part of the course, which was a bunch of intro and supervised learning. Then we went to unsupervised learning for a bit, and now we're back in supervised learning. And we've been talking for several weeks already about linear models, and believe it or not, we're going to spend one more week talking about linear models, which is this week, because there's really a lot to say. And as you hopefully recall, even though you just came back from your break, we're talking about models whose predictions are a weighted sum of the features, and we are trying to learn those weights from training data. And we talked about regression so far, linear regression. So linear models for regression, meaning that our target or our y variable is numerical. And we talked about how in that case we didn't want to just check if our input was equal to our output, which is sort of what we were doing in the part 1 of the course with classification. And so we were using, for example, squared error and minimizing that. And then we got these normal equations for finding w, and we also talked about gradient descent. So we talked about that. We talked about a whole bunch of norms and their implications. So a simple change from an L2 norm to an L1 norm can change the results quite a bit. And when we made that change in our objective function, we got regression that was robust to outliers in the targets. And when we made that change in regularization, we got this sparsity-inducing regularization, or regularization that did feature selection for us. So after that, we talked about nonlinear regression. Or I don't know if after or before, but at some point we talked about nonlinear regression using the machinery of linear regression by changing our basis or changing our features or whatever you want to call it. So instead of directly fitting, say, a quadratic model, we'll just make a new feature that's x squared, and then we'll get the same behavior. We also talked about the RBF basis. We'll be talking a little more about that next week. Okay. We did a lot of things lately, apparently. We talked about feature selection, and we used that as our basis for coming into regularization. So we had search and score for feature selection, and forward selection, meaning let me try adding a feature, picking the one that is best based on some score. And then we went from there to regularization. So we said we could think of this as L0 regularization. What happens if we do L2 or L1 regularization. Okay, so that summarizes the stuff we have already done on linear models. And as I mentioned, we're now going to talk about linear models for classification. Okay. And yeah, I guess I already said this. Seems like we're spending a lot of time on this, but these things are used a lot, and they form building blocks for other things we're going to talk about. Okay, so that was the review. You now can't pretend like you've forgotten everything from the first part of the course just because you were off of school for a week. So let's jump back into things. This is a picture of Mark Schmidt's email inbox. And the question is, what about those stickers saying this email is important or not? Or we also talked about spam filtering earlier on. So this is a classification problem. We've already talked about some ways of doing classification, such as decision trees, KNN, etc. Gmail, as it turns out, uses something called logistic regression, which is something we're going to talk about today, which is a type of linear classifier. So this week, we're going to be careful about encoding our positive examples as +1 and our negative examples as -1. It didn't matter until this week. We could have said, I don't know, sick, not sick, spam, not spam, 0, 1, 1, 2, A, B. But we're going to be careful about calling them -1 and +1 this week because it's going to give us some nice mathematical conveniences if we do that. And remember, today we're going to be talking about predictions. So here's how I'm going to make predictions. I'm going to compute W transpose X, and I'm going to get some Y, but that Y is going to be any number. It's not going to be +1 or -1. But I'm going to try to use that output of the linear model to do classification for me. And here's the plan. It's not that crazy. We're just going to look at the sign of the thing. We'll say, okay, we're going to fit linear model, compute W transpose X. If it's positive, then we predict +1, and if it's negative, we predict -1. That is, in fact, mostly the point of today, except as usual, it's always not quite as simple as it seems. Yes, you now know how these models are going to make predictions, but we still have a lot to talk about. Any questions, though, or comments about this? It's been a while. Tom?
What happens if it's 0?
What happens if it's 0? We don't really have to worry about that case. It's one of those very unlikely situations. I suppose if all your weights are 0, it's going to be 0. So let's call that an implementation-dependent detail. You can pick randomly or pick one or the other. So by the way, this is why we want to write y as +1 or -1. Now we can just say yi is the sign of W transpose X, where the sign refers to being + or -1. Any other thoughts? Okay. So imagine we just have one feature, and now when we plot y, it's only going to be +1 or -1. It's not going to be all over the place like in regression. And our boundary in one dimension is just going to be some threshold. We're going to say If x is bigger than that, we want to predict not important. If it's smaller than that, we want to predict important. But you should be thinking about that as there is some linear fit underlying that threshold. So this would be the W I would want to learn, is this slope. So that when my output of my linear model, in this case just a line with one feature, is negative, I'm going to predict -1, and positive, I'm going to predict +1. Next. Philip.
Is there a way to, is it reasonable to use the magnitude of the value as sort of a probability of...
Is it reasonable to use the magnitude of the value as sort of a probability? Yes, we will talk about that today. It's very reasonable. Okay. Please ask a question or raise your hand if you're confused about this green line, because it's kind of a fundamental aspect of what we're doing today. Yeah, Ari? No, wait. Okay, what's your name again?
Amit.
Amit, yeah.
In that picture, maybe it's just the picture, but it looks like the only thing that matters is the intercept.
In this picture, it looks like the only thing that matters is the intercept.
Or the x-intercept.
Well, that is true. The only thing that matters is the x-intercept. And in general, in higher dimensions, we are going to have some plane in higher dimensions. And what we're going to want to know is, when does W transpose x equal 0? That is like the x-intercept in higher dimensions, because that is going to be our boundary. And because everything is linear, that boundary is actually going to be itself a hyperplane. In this case, just the boundary is 0-dimensional, I guess, just a point. Except what Philip said is we are going to end up also caring about more than that, because we're going to use the magnitude for something as well. Okay. So here the boundary is just a point. Here's what our predict function looks like. It's taking the sign of the output of the green line, and this thing is getting 0 training error. So this is sort of a linear algebra fact or a calculus fact, or somewhere it appeared in some math course that the W transpose x equals 0 defines a hyperplane, or theta dot x, or theta dot r, or you saw it in some form, maybe. That it's a geometrical fact that this defines a hyperplane. Okay. So, as you know, I like to show these types of pictures. So we've seen this, and now we have a linear classifier. So before I was showing it to you in one dimension, here is a major potential for confusion here. The last slide I showed you a line, a green line. On this slide on the right, I'm showing you a line. They are not the same. In the first case, I was showing you one feature and the actual W transpose x, which we are then going to throw away and just take whether it's positive or negative. Here I'm showing you a universe with two features. And now W is two numbers, not one number. And that line I'm showing you there is W transpose x equals 0, like it says on the slide. And there is some plane coming out through the slide, which is that model output W transpose x. And then we only care, like Amit was saying, where it equals 0 when we're drawing this type of picture. So when we say linear classifier, this procedure I just described, take the sign of W transpose x, corresponds to take a hyperplane and cut the space in two with a straight line or plane in higher dimensions. Yeah.
What are the axes in
Allie.
these pictures?
What are the axes in these pictures? The axes are, and it's a good point, they should be labeled. The axes are two features. So we're either just assuming we only have two features in our data set, or we're just looking at two particular features. So one feature, another feature, and then decision trees are doing thresholds on the features. KNN is doing some weird non-parametric thing. And here we're just cutting the feature space in half.
Okay.
Yeah, I don't know your name. Or is it Laura? What's your name?
Laura,
Laura.
would there be an issue treating very large magnitudes as high probabilities because they're probably extrapolations?
Say that again a bit louder.
Would there be an issue treating very large magnitudes as high probabilities of certainty because they're probably extrapolations?
Would there be a problem treating very high magnitudes as very high probabilities because you're extrapolating? Good question. We will talk about that. We will let regularization enter the picture there, but let's put that off for a moment. Any other questions? Edwin,
But if
you forgot everything in a week and I forgot all your names in a week. Okay, yeah, go ahead.
If we have more red points on the bottom right corner of the picture, isn't it the case that the linear classifier is going to produce a non-zero training error?
Yes, correct. This data set I gave you is what's called linearly separable, which means there exists a linear classifier that gets zero training error. You are correct. If I had a red point, say at the bottom right, or even worse, the bottom left, then that wouldn't be possible, which is different from decision trees, different from KNN. In those universes, other than really crazy situations, we could get zero training error. We didn't want to necessarily because we'd be overfitting potentially, but we could. You're right, this is in a sense a new situation for classification that we cannot get zero training error here, in fact, for most data sets. So this is sort of a broader question of, is this a very underpowered classifier because it can only learn ridiculously simple boundaries? And there's many answers to that, which we'll be answering throughout the week and next week. One answer is we only have 2 features here. So in a sense, the more features we have, the more dimensions we get to play around with when we cut the space in half, even though it's pretty hard for us to visualize that. And I think I talked about that in my bonus lecture. I don't know if anyone watched it, but I talked about that with linear regression, which is a very similar situation. Like, what does it mean to overfit when my model is linear because the model is so simple? Another answer to your question is we talked about this basis transformation stuff to make linear models nonlinear. Next week on Monday, we'll talk about an equivalent thing here and make some progress on that as well. That's a good point. Okay. The perceptron algorithm is not something I expect you to use. It's just something I expect you to know about. So you don't go into the world saying, hey, I took a machine learning class from Mike, and then someone says, oh, perceptron, and you say, oh, I've never heard of it. So for my own selfish interests, I'll just allow you to hear about it. But it's more of a historical note at this point. And it's an early supervised learning algorithm. It is a linear classifier. So in fact, for the purposes of today, it is exactly what we're talking about. What's different about it from modern methods is how it's trained, which is, well, mainly, the main difference is how it's trained, which is what we're going to talk about on Wednesday. But the spirit of it is pretty much exactly our stuff today. So search for W such that sign of W transpose Xi equals Yi for all I. The perceptron was conceived for a linearly separable data set, which I just described. And it was guaranteed to get zero training error in that case. So now that I'm looking at this, I feel like this might have been more appropriate for Wednesday. It doesn't matter that much. But this is now a training algorithm, which I said I wouldn't talk about. In any case, you start with some initial W. Let's start with 0. And you go through your examples until you make a mistake. And then when you make a mistake, you update W by adding that training example to it, if it was positive, or subtracting that training example from it if it was negative. And then you just keep going over and over and over again through the data set, and this is guaranteed to converge on something with zero training error if the data set is linearly separable. So the idea, the intuition of why am I adding x to w, what do they even have to do with each other? The intuition is, think about I make a mistake. I have a positive example, I say it's negative, so I'm going to add x to w. Well, what does that mean? It means my new w is w plus x. And what happens if I try it again on the thing I just failed at, which was classifying x? I'm just going to try again right after. Well, I'll get w plus x, which is my new w, dot product with x, which is w transpose x, my previous prediction that failed, plus x dot producted with itself, which is some non-negative number. So I made a mistake. I was supposed to output some positive thing bigger than 0, but I outputted less than 0. So I'm wrong. By adding x to w, and I just try again, I will get something hopefully bigger. I guess if x is 0, it would be, but that's not really. Let's assume the x are non-zero. Then I get something bigger. And now I should do better. And it doesn't mean I'm going to get it right, because maybe I didn't increase it by enough. But if I keep doing this over and over again, I'll eventually converge, and you can prove this. Yeah.
How is it not messing up previous one?
Yeah. No, it's a good question. I haven't gone through the proof. But Fed asked, how is it not messing up previous examples? It's true. I was doing great on everything else. Now I just added x to w. I have to use that same w for all my predictions. So it is a non-trivial fact that this actually works. It's not just super obvious because of this issue that you raised, right? So it's true and interesting and was a big deal at the time, and is sort of a precursor for stuff we're talking about this week, but also a precursor for neural networks and deep learning that we're going to talk about later in the course. Okay. Right. We have time. This is good. Halfway done. So I don't know. I guess this is officially a demo, but it's really more like the other half of the lecture. It's a bit more fleshed out than most of the demos, I guess. Okay. Oh, no. I can deal with this. Don't despair. Okay. This plot classifier is not a standard thing. It's just some code I have that's adapted from scikit-learn. It's the code that produces those plots we've been looking at with the, yeah. Okay, but I just had it in the wrong directory. Okay. So this part, how's the font size in the back?
Can you squeeze a little bit, please? Thank you.
Okay. So this should not be surprising you. It's just what I've been saying. You predict by taking the sign of W transpose X. And there's this issue of the intercept, which I've kind of been avoiding. It's the exact same thing as the intercept with linear regression. I can add this column of 1s to X, and then it's the same thing as having an intercept. So if I write it like this, it's not because there is no intercept. There definitely is, right? But I just don't have to write it if I play this trick. And then if I'm implementing it, I could implement it like this as well. Although you have to be a bit careful when you're implementing. We talked before about regularization and should you regularize the intercept. And if you're not careful and you implement it with the column of 1s, the regularization will treat the intercept W the same as all the other W's. So just something to think about. OK, here's the usual toy data set. OK, let me show you what I'm doing. Generating data set, calling scikit-learn's logistic regression. I probably should have said that at some point. Logistic regression and support vector machines are the two linear classifiers that we're going to be talking about. Just instead of going lecture on logistic regression, lecture on support vector machines, we're just doing predict for both of them and then fit for both of them. OK. So here's what I'm doing. Model.coef and intercept in scikit-learn are where the goods are stored, the weights. I am writing to those things. So whatever happened in fit, I'm just obliterating that and saying, you know what, I want my own coefficients. And then I'm plotting it. And the beauty of this is we can now, what I really want to accomplish in today's lecture is for you to get a feel for what do the coefficients mean. Because with linear regression, it's a bit easier, at least for me, to get a feeling for the interpretation of the W's. W5 says if I increase feature 5 by 1 unit, the output increases by W5, right? But let's try to get a feel for the coefficients here. So here's -1, 1. Someone call something out, and I'll change it to that. Slope or intercept. Whatever you want.
Intercept -1.
Intercept -1, OK. So I changed the intercept. I have shifted my decision boundary. I can make it -3. I can make it -4. So you see where this is going. I can make it +3. And if I make it 0, then the boundary is actually passing through the origin, which makes sense. Because if my intercept is 0, then when x is 0, 0, W transpose X is going to give me 0, which giving me 0 meaning it's on the boundary. So again, remember, there is a plane coming out of this board at some particular angle, and the line is W transpose X equals 0. OK, so that's what the intercept does. Shifts. Kind of makes sense. It shifts orthogonally to the plane. OK, now you must all be wondering what the coefficients do, and you probably suspect, right? So let me try this. Change -1, 1 to -1, 2. Maybe -1, 5. Maybe 0, 5. So I'm changing the slope of the thing. And again, in higher dimensions, the hyperplane has more slopes, right? If I have d features, I have a d minus 1 dimensional decision boundary. Like here I have 2 features, I have a 1-dimensional boundary, meaning a line. Philip.
Since this is a two-feature plot, shouldn't there be 2 steps?
Ha, right. OK, since Philip asked, since this is a 2-feature plot, shouldn't there be 2 intercepts? No. So think back to linear regression from a couple weeks ago. We just had one intercept no matter how many features there are. It was like the overall shift, and then the coefficients were the slopes. So it's the same thing here. We have some w's, some coefficients controlling this, and then the intercept is an orthogonal translation, and we don't need more than one. Edwin.
Is the cutoff plane always perpendicular to the feature plane?
Sorry, I just want to disable this saving because it really annoys me. Just a minute. Okay. Is the cutoff plane always perpendicular? Do you mean... Does that answer your question?
No.
Okay, so what's your question?
So we're looking at 3 dimension, right? So say this dimension is the y dimension,
Okay.
and this is x1 and
Okay.
x2,
Yeah.
and then is the cutoff plane always perpendicular to the features dimension?
Yes. I think I know what you're asking. Okay. We have some plane coming out of the board that, honestly, it's not always useful to think about it that way. It depends. You should be aware of it, but the decision boundary is always in this feature space. However many features we have, it is a hyperplane cutting that space in half. So yes, setting y equals 0 will become a plane in X space.
The reason I'm asking is there would be some kind of data where it's not separable by these kind of
Yeah.
separable by these kind of plane. So how do I get a plane like
Any possible line is allowed here. We can learn any possible line, 360 degrees of rotation, by changing those coefficients. We just cannot learn anything that's not a line. Tom?
I think he's a little confused in that he thinks that there's actually a plane with an angle coming out this way in a 2D space. He's talking 3D, right? This is just one line, right? There's no angling of that line. It has no second coefficient of...
Oh, that's the... Okay, I think we're getting at something that I wanted to talk about anyway, so let's talk about it. I'm still not exactly sure, but let me try this. What may be bothering you is that I have 2 coefficients here, and yet you're thinking, hey, this is just a line. Why do I need 2 coefficients? Why don't I just need one number? And indeed, look, this is minus 5, 5, but what if I do minus 1, 1? What do you think is going to happen?
Same thing.
Right. So maybe this is what's bothering you, Edwin, or if not, we can talk about it later. But there is a redundancy here, because we should only need one number to represent the slope of a line, and we will tackle that redundancy before the end of today. Oh, by the way, what happens if I do change the sign? Right. If I change the sign, I flip blue and red. Because, remember, my prediction is the sign of W transpose X, and I just took W and multiplied it by -1. So everything's the same except the sign is flipped everywhere. So +1s become -1, -1s become +1s. If you were wanting this rather than that, and I saw some of you doing that sort of hand signal, if you want that, then you need the 2 coefficients to be the same sign as each other. Okay, so one thing we can do here, just for fun, so we did that, okay, is I can just run logistic regression itself. And here's what scikit-learn logistic regression gives us. And on Wednesday, when we talk about the loss function and how it picked that to be the best line, we'll understand in detail why that was chosen, how regularization is going to affect it, and so on. Because I more or less turned off regularization there. And we can also talk about support vector machines. And it learns something slightly different than logistic regression. We'll understand that on Wednesday. By the way, scrolling up for a minute, By the way, I could have done this. I could change, here it doesn't matter, I was hijacking this scikit-learn function and just writing to its coefficients and using its predict function. So this plot classifier calls the predict function. So I could change from logistic regression to linear SVM. And I just want to show you it's the same. At least I think it was it? It's hard to see.
I think the data points change.
Yeah, it's regenerating the data.
Oh, it's regenerating the data. Thanks. Good to have you guys on my side here. Okay, thank you. Not regenerating data points. Good. So that's a very important thing I want you to take away from today's lectures. Logistic regression support vector machines have different sounding names. They have the exact same predict function because they are both linear classifiers. Their predict function is literally sine of w dot x. So the difference between them comes on Wednesday. For now, we don't care. We just want to talk about linear classifiers today. You could, in a sense, they are two different loss functions for the same model. Ish. Yeah, okay. Okay. Scrolling down, looking at the time, it's pretty good. Okay. Right. Good. So I guess as a preview on Wednesday, when we're making errors like we are here, we'll have to think about how to trade off different types of errors when we come up with loss functions. Okay, scrolling down. Oh, I already did this here. Okay, we'll skip that. This was just showing the equivalence, which I already showed. Okay, now we get to the moment that Philip has been waiting for, which is these probabilities. So my plot classifier function was calling predict. Let me just call predict so you can look at it. It's what you would expect, a bunch of minus ones and plus ones. That's what it's supposed to do. But there's also the ability to predict probabilities. This happens to be called predict proba in scikit-learn, but doesn't matter what it's called. What this is returning is probabilities for the two classes, and you'll notice they add up to 1. Which makes sense. It's either this or that. So you might think it's a bit redundant that it returns both. Fine, we can get over that. But this is nice. We have not talked too much about this in part 1 of the course when we talked about KNN and decision trees. Although it is possible to coerce those things into giving you probabilities, it's especially natural here. And that's useful information, right? If you're 49% confident versus 0, or I guess I should say 51 versus 99.9, tell me, please. Don't just say plus 1, right? I would appreciate that information from my classifier. Maybe sometimes at the end of the day I cannot use that information because I have to make a decision. Fine. I will threshold the probability at 0.5. But maybe I do want that information. Doesn't hurt. Okay, so in my plot classifier function, I added a flag there to say it's the exact same code roughly, except I swapped out predict with predict proba, and then I make the same picture. And this is a contour plot. I guess this isn't my latest version of plot classifier, but it doesn't matter. So this gets the job done. It just keep in mind it's actually a smooth change in probabilities, even though it's showing levels. That's just the visualization issue, but it's really a smooth process. And right in the middle here, in the middle of this white band, is what we were before calling the decision boundary. I'll get the prettier pictures when I post it online. But OK, not quite as pretty as I'd hoped, but you have the probability contours. Yes?
Sorry. So you say that it's continuous. There's that dark blue area there. That is it. Does it increase as it goes outwards totally, or is it just in that central area?
Yeah, it decreases smoothly. That's why I wanted the improved version of the plotting code.
Even in the areas with just blue and just
Yes, it's a smooth decrease everywhere. OK, so what we have here is a richer plot than what we had before. It still contains the same information than what we had before, in the sense that in the middle of that white band in the middle is our old decision boundary, and that's probability 0.5. So setting the sign, looking at the sign of W transpose X is the same as looking at the probability being more than or less than 0.5. And then as we go all the way this way, we get more and more confident that it's red. And as we go that way, we get more and more confident that it's blue. Yeah, all right.
Why is that? Is that part of the data?
Yeah, how do we get that? So,
because I could imagine a line splitting through and then like 3 blue points on the other side relatively close.
OK, the way we get this is basically by looking at the distance from the boundary. So there's some fixed formula, which I'll show you in a minute. And it basically says at the boundary, you're 0.5. And the farther you are from the boundary, you approach probability 1 and 0. That's it. It doesn't look at anything else.
No, I'm saying, but why are we allowed to say that about the data? Like, why can we?
Why are we allowed to say that? OK, so there is a statistical interpretation of logistic regression that you would see in a statistics course if you're talking about generalized linear models. You make an assumption about the distribution of the data. You say, I'm getting the weights using maximum likelihood, and there's kind of a coherent framework. But we're not really talking about that here until a couple of weeks from now.
Okay.
Yeah, OK. So what I wanted to do is we talked about how we had that extra coefficient. So we only needed one number to get the slope of the line, but I said if I had 1, 1 or 5, 5, I was getting the same answer. And now we can interpret the scale of the coefficient. So here's what I'm going to do. I'm going to take the coefficients and multiply them by 2, and then make the same plot. And you'll see that in the new plot, the bands are a lot tighter, meaning I'm more confident, because there's a bigger part of the space where I'm very close to 100% probability. So bigger coefficients mean I'm more confident, because I'm actually looking at that number, W transpose X, to get the probability. And if I multiply W by 2, my W transpose X number is going to be bigger everywhere, and so my probability is going to be more extreme everywhere. And I can also make the coefficients smaller. And I get this very cautious, probabilities between 0.4 and 0.6. I don't really know. I just kind of think this and think that. And the reason why this is nice is it gives us an interpretation for regularization. Because regularization, as we talked about 2 weeks ago, makes coefficients small. That's what it does, right? And we had a bit of a hard time interpreting that sometimes, like for linear models. But here we have a clear interpretation. Small coefficients means less confident. It means probabilities hanging around 0.5 and not going to 0 and 1 really fast. And that kind of makes sense in the sense that overconfidence and overfitting are related concepts. And so regularization is keeping that in check to some extent. It's also changing the boundary, but it's also changing our confidence in our predictions. OK, so I don't have time for any more questions. So I just want to show you the last thing, which is this sigmoid function, which is how do I get from W transpose X to a probability? So this is the function. It's 1 over 1 plus e to the minus x, so it's shown up here. And it has the properties that make sense to us. At 0, it crosses 0.5. So when I would have predicted positive or negative by crossing 0 with W transpose X, sorry, I should scroll up a bit so you can see the labels. Then I'm crossing 0.5. So in other words, when I would have predicted +1, my probability of +1 is above 0.5, and when I would have predicted -1, my probability of predicting the positive class is less than 0.5. So thresholding at 0 is like thresholding at 50-50 probability, which makes sense. And it's monotonic, that makes sense. And so this axis, here you can think of as distance from the boundary. And as I get farther and farther from the boundary, here I asymptotically approach completely confident in predicting one thing. And as I get farther and farther from the boundary in this direction, I asymptotically approach complete confidence in the other thing, which is the same as saying 0 probability for the other class. Okay. So let's just summarize. Today we talked about binary classification using linear regression and how this W transpose X can give us something useful for classification. We can look at the sign of it to make a prediction. The intercept is like an orthogonal shift in where the plane is. The coefficients control not only the angles of the plane, but there's this extra level of redundancy, which ends up encoding, in a sense, the confidence. In that if all my coefficients are ridiculously huge, then all my values of W transpose X will be ridiculously huge, and I'll be at those ends of that S curve that we saw, which means I'll always be very, very confident. And if my coefficients are very, very tiny, my probabilities will be very close to 0.5, meaning I'm not confident. We talked about the perceptron. We didn't talk about this, but we will on Wednesday. So on Wednesday, we will talk about what is logistic regression, what is support vector machines, how do I fit those lines, and what are the different loss functions.